settle into the sleepy mind channel. Tonight, we will slowly explore one of the most unusual places on Earth. Far out in the sea, surrounded by bright water and long coral reefs, there is a dark circular opening in the ocean that appears almost unreal when viewed from above. If you like stories like these, feel free to like and subscribe. More videos on interesting topics are posted weekly. At first glance, it looks less like part of the sea and more like a giant doorway cut into the planet itself. The water surrounding it glows with soft shades of turquoise and pale blue, yet the center appears dark and endless, almost like a quiet eye resting beneath the surface of the ocean. The Great Blue Hole is not simply a deep patch of water, it is a massive underwater sinkhole located off the coast of Belize. From the air, its nearly perfect circular shape immediately captures attention, because nature rarely creates formations that appear so balanced and symmetrical. Yet every part of it was created slowly through natural geological processes operating over time. The surrounding shallow water is filled with sunlight, reflecting off sand and coral reefs beneath the surface. That reflection creates glowing shades of aqua and light blue that feel warm and calm. Then suddenly, in the middle of those bright tropical colors, there is a deep navy circle where light struggles to reach far below the surface. The Great Blue Hole rests within a larger coral reef system called Lighthouse Reef. Coral reefs grow slowly over time and often create complex underwater structures that support enormous amounts of life. From above, the reef appears almost protective, forming a natural ring around the darker center. In calm weather, the ocean's surface around the area can become incredibly smooth, allowing the colors to stand out even more clearly. Sunlight reflects gently across the shallow reef, while the darker center remains still and mysterious. Without boats nearby, the formation can look small from photographs. In reality, the blue hole stretches more than 300 meters across. Standing at the edge of it, in a small boat, can feel similar to standing near the rim of a giant natural crater. The water changes color almost immediately, shifting from bright tropical blue into a darker shade that suggests sudden depth below. What makes the blue hole even more fascinating is that its story did not begin underwater at all. The formation visible today is only the latest stage in a much older history, shaped by rainwater, stone, caves, rising seas, and changing climates. Millions of small geological changes slowly combined over time until the blue hole emerged. What appears peaceful and still today was shaped through long periods of transformation that unfolded so gradually, no human being could ever witness the entire process in a single lifetime. From above, only the opening is visible. The deeper history remains concealed below layers of water and stone. Divers who descend into the blue hole often describe the experience as entering another environment entirely, because the brightness of the surface slowly fades while the walls descend vertically into darkness. Yet even before reaching those depths, the view from the surface already tells part of the story. Tonight, we will gently explore how this remarkable place came into existence, how changing sea levels transformed dry land into submerged ocean terrain, how caves formed deep underground before flooding with seawater, and how life now survives around the edges of this giant marine sinkhole. We will look at coral reefs, ancient limestone, underwater conditions, geological time, deep water environments, and the quiet processes that shape the Earth even now. The blue hole may appear frozen and unchanging from above, yet it remains part of a planet that is constantly moving, shifting, dissolving, growing, and transforming one slow step at a time. Around the outer edges of the blue hole, the Caribbean Sea becomes much lighter in color. The water shifts from deep navy shades into glowing turquoise and pale blue tones that seem almost illuminated from below. The darker center appears calm and heavy, while the surrounding water looks bright, warm, and almost transparent. Nature created a scene that resembles a carefully painted image, yet every shade and boundary is controlled by depth, sunlight, coral, and the shape of the seafloor itself. The lighter water surrounding the blue hole exists mainly because sunlight can easily reach the shallow reef below the surface. In tropical oceans, shallow water often appears bright because light reflects off white sand, limestone, and coral structures resting beneath the sea. When sunlight enters clear, shallow water, many of the lighter wavelengths bounce back upward toward the surface. Human eyes then interpret those reflections as glowing blue and turquoise colors. In deeper water, however, sunlight struggles to travel downward. More light becomes absorbed before it can return to the surface. The result is darker water that appears heavy and shadowed even during bright daylight conditions. On one side, there is bright tropical reef water filled with reflected light and gentle color. On the other side, there is deep darkness, where the ocean floor disappears from sight. The dividing line between those environments appears surprisingly sudden from above. Boats crossing near the outer rim often pass from bright blue water into darker water within only a short distance. To human perception, sudden changes in color naturally create curiosity, because the brain immediately recognizes that conditions below the surface must be changing rapidly. Rivers carrying mud and soil can darken coastal water in some regions of the world, but around Lighthouse Reef, the water frequently remains clear enough for sunlight to penetrate deeply into the upper layers. This clarity allows the reef colors to stand out strongly during calm weather. Pilots flying over the area sometimes describe the surrounding ocean as appearing almost luminous under direct sunlight because the shallow reef reflects light so effectively. The coral reef surrounding the blue hole forms part of a much larger living marine system. Coral reefs are built gradually by tiny marine animals called coral polyps that create hard calcium carbonate skeletons over time. Generation after generation of coral growth slowly builds large reef structures that can eventually become visible even from space. Although reefs may appear similar to underwater rock formations, they are actually living ecosystems filled with countless interacting organisms. Fish, algae, crustaceans, mollusks, and many other forms of marine life depend upon reef environments for shelter, food, and protection. The reef system also serves another important role beyond appearance, because it protects portions of the inner area from stronger ocean movement. Coral reefs often function like natural barriers that absorb wave energy before it reaches more sheltered water behind them. Over long periods, reef systems shape coastlines, influence water movement, and create calmer environments where additional organisms can thrive. It forms part of the environmental system that defines the region itself. The dark circular opening now hidden underwater did not yet exist as a marine formation. There were no coral reefs surrounding deep blue water, and no divers descending into darkness beneath the surface. Instead, During past ice ages, this area stood exposed beneath open air as part of a dry limestone landscape stretching across the region. What is now ocean floor once existed as solid ground shaped by wind, rain, temperature changes, and slow geological forces operating over time. Ice ages changed the appearance of the Earth in dramatic ways because vast amounts of water became trapped inside enormous continental ice sheets. Thick glaciers spread across large portions of North America and northern Europe, storing so much frozen water that global sea levels dropped significantly. Coastlines shifted outward as shallow ocean regions became exposed land. Areas now covered by tropical seas once formed plains, rocky terrain, caves, valleys, and dry coastal environments. At the time these ancient changes were unfolding, the exposed limestone landscape around the future blue hole would likely have resembled rocky tropical terrain shaped by rainfall and gradual erosion. Limestone is a relatively soft sedimentary rock made largely from calcium carbonate, the same material found in shells, coral skeletons, and many marine organisms. Over immense stretches of time, thick layers of marine sediments compressed together and hardened into limestone formations across the region. Once exposed above sea level, those limestone surfaces became vulnerable to weathering and chemical change. Rainwater played one of the most important roles in shaping what would eventually become the blue hole. Although rain may appear gentle compared with earthquakes or volcanic eruptions, water possesses enormous long-term geological power because it operates continuously over time. Rainwater naturally absorbs small amounts of carbon dioxide from the atmosphere and soil, creating a weak carbonic acid solution. When this slightly acidic water moves across limestone, it slowly dissolves tiny amounts of rock. Caves, sinkholes, underground rivers, and natural stone chambers often form when water dissolves pathways through limestone beneath the surface. In some places, entire cave systems stretch for hundreds of kilometers underground. At first, rainwater may seep only through small cracks within the rock. Over time, however, those cracks widen slightly as more limestone dissolves. Water then flows more easily through the enlarged openings, accelerating the process even further. Small fractures slowly become tunnels, chambers, and underground passageways. The future Great Blue Hole likely began through this same quiet process. Rainwater gradually moved downward through exposed limestone terrain, dissolving the rock little by little over enormous spans of time. Unlike sudden natural disasters that unfold within minutes or hours, cave formation happens so slowly that no human observer could witness the full transformation. Entire generations would pass while only tiny changes occurred. Yet given enough time, those tiny changes accumulated into massive underground structures hidden beneath the surface. In many limestone cave systems around the world, the surface above can appear calm and ordinary, while enormous empty chambers slowly form below ground. Forests, grasslands, and rocky plains may sit above hidden caves without revealing what lies underneath. The same was likely true in the ancient landscape that eventually became the Blue Hole. Beneath the exposed limestone surface, water slowly carved larger underground spaces through chemical erosion, while the land above remained relatively stable. As sea levels remained lower during Ice Age periods, these underground cave systems expanded within the dry limestone terrain. Air-filled chambers stretched beneath the landscape, while mineral-rich water moved through cracks and tunnels inside the rock. Some sections may have contained underground pools or streams, flowing through darkness far below the surface. The environment would have resembled a hidden subterranean world separate from the future environment that would later flood the region. The underwater sinkhole visible today originated from processes that began long before seawater covered the area. The shape of the structure, the steep walls, and even mineral formations discovered deep inside all point toward its history as a former cave system exposed above sea level. The ocean eventually transformed the landscape, but it did not erase the earlier geological story hidden within the rock itself. Beneath the limestone landscape that once existed above the future blue hole, underground caves expanded through darkness. Water moved silently through cracks and passageways within the rock, gradually dissolving more limestone as centuries passed. At first, many of these underground spaces were likely narrow and uneven, shaped only by small amounts of flowing water, finding weak points inside the stone. Yet geological processes rarely remain fixed for long periods. As more limestone dissolved away, water gained access to larger pathways, allowing the underground cave system to expand steadily over time. Cave formation depends heavily on patience and repetition. Rain falls onto the land. Water sinks downward through cracks in the limestone. Small amounts of rock dissolve. Water continues moving through the same pathways again and again over time. Eventually, those repeated movements begin reshaping the underground structure. At first, the change is barely noticeable, yet steady repetition eventually transforms the landscape. As underground spaces widened, structural changes gradually developed inside the limestone terrain. Some cave chambers likely became large enough to support underground pools of water, while others formed long tunnels connecting separate sections together. In many limestone cave systems around the world, underground chambers eventually grow large enough to resemble enormous natural halls hidden beneath the earth. Some contain ceilings towering far overhead, while others stretch outward into networks of branching passages extending deep underground. Inside these ancient caves, the environment would have remained cool, dark, and quiet compared with the tropical climate above the surface. Without sunlight reaching inside, there would have been no ordinary plant life growing within the chambers. Water dripping from cave ceilings slowly carried dissolved minerals into the underground spaces. Over long periods, these minerals could begin forming stone deposits hanging downward from the ceiling or rising upward from the cave floor. The foundations of features later discovered deep inside the blue hole were already beginning to develop during this ancient dry period. The limestone itself also influenced how the caves expanded. Limestone contains natural variations in strength and structure, meaning some sections dissolve more easily than others. Water naturally follows the weakest available pathways, enlarging fractures and softer zones first. Over time, this creates irregular underground chambers, where some walls remain thicker and more stable, while other sections become thin and vulnerable. Structural balance within caves is constantly changing as erosion slowly removes supporting rock. Mineral deposits inside caves often form in layers, almost like natural archives, slowly recording changes in water movement and climate over time. The caves beneath the future blue hole likely experience changing moisture levels, shifting underground water flow, and gradual expansion as the surrounding environment evolved across different climate periods. Although the surface world above changed with temperature and rainfall, The underground chambers remained isolated and still. As the caves expanded, some ceilings likely began carrying increasing structural stress. Limestone rock above large underground chambers can remain stable for long periods, but eventually certain sections weaken as supporting material disappears below. The larger the underground spaces became, the greater the pressure placed upon the remaining rock overhead. Yet even these structural changes unfolded gradually. Small fractures may have spread slowly across cave ceilings long before any major collapse occurred. Roads, forests, and fields can suddenly drop downward into underground spaces once the supporting rock becomes unstable. The process responsible for those modern sinkholes is related to the same geological forces that shaped the future blue hole, though on a much larger scale. Long before the Caribbean waters flooded the area, the underground cave system beneath the limestone terrain was already growing larger and structurally more complex. The underground cave system beneath the limestone landscape eventually became large enough that the structure above could no longer remain permanently stable. Hidden chambers continued widening while the rock overhead carried increasing pressure. The surface world above still appeared calm and solid, yet deep below, the geological framework was slowly approaching a turning point. Water had already shaped the underground spaces. Time had already weakened portions of the limestone. The next stage of transformation was beginning to approach within the hidden darkness below the ancient Caribbean landscape. As the underground cave system beneath the limestone landscape expanded, the rock above those chambers slowly became less stable. Large empty spaces had formed beneath the surface after countless years of chemical erosion dissolved sections of the limestone away. The ceiling above the cave still appeared solid from the outside, yet deep underground, the balance between support and pressure was gradually changing. The wider the cave chambers became, the more weight the remaining limestone ceiling needed to hold above the growing void below. Rock can appear permanent and unchanging during a human lifetime, but even stone responds slowly to pressure, fractures, moisture, and time. Water moving through fractures could weaken portions of the limestone further, while gravity constantly pulled downward on the unsupported rock overhead. The underground chambers beneath the future blue hole were no longer small, narrow caves. They had become large structural spaces hidden below the exposed landscape. Eventually, portions of the cave roof could no longer support the weight above them. Sections of limestone collapsed downward into the underground chambers below, creating a massive sinkhole exposed beneath the open sky. The process may not have happened all at once. Different sections of the cave roof likely weakened and failed over extended periods as structural pressure shifted through the surrounding rock. Over time, the underground cave system transformed into a large open depression connected to the surface world above. The newly formed sinkhole would have looked dramatically different from the underwater blue hole visible today. Instead of dark ocean water filling the opening, there may have been steep rocky walls descending into a dry limestone basin exposed to air and weather. Sunlight reached areas that had once remained hidden in darkness underground. Broken rock from collapsed cave ceilings likely rested across portions of the floor below. The formation visible at that stage represented a transition between underground cave and future marine sinkhole. For a period of time, the sinkhole likely remained exposed above sea level as part of the dry limestone terrain surrounding it. Wind, rainfall, temperature changes, and erosion continued affecting the newly opened structure. Water may have collected temporarily inside portions of the depression during storms or seasonal rainfall, though it was not yet permanently connected to the sea. The walls of the sinkhole exposed fresh limestone surfaces that had once remained hidden underground for immense spans of time. The environment surrounding the sinkhole during this ancient period would have looked different from modern Belize. Sea levels remained much lower because large amounts of water were still locked inside continental ice sheets around the world. The coastline existed farther away from the future blue hole than it does today. Areas now covered by shallow Caribbean water may have appeared as dry, rocky plains, exposed reef platforms, or coastal limestone terrain stretching outward toward the distant sea. Then slowly, global climate conditions began changing again. Temperatures gradually warmed as major ice age periods came to an end. Massive glaciers covering large regions of the Earth started melting over time. Water that had remained frozen for thousands of years slowly returned to the oceans, causing sea levels across the planet to rise. Coastlines shifted once again as ocean water gradually flooded lower elevation regions around the world. Eventually, seawater reached the large collapsed sinkhole itself. Water slowly began filling the depression, transforming the once dry geological structure into a submerged marine feature connected to the surrounding Caribbean Sea. The same opening that had once exposed underground cave chambers to sunlight now descended below the waterline instead. The sinkhole entered an entirely new stage of existence, shaped no longer by dry land conditions alone, but by the interaction between ocean water, depth, light, and ecosystems. As water levels continued rising, the sinkhole became fully submerged beneath the sea. It remained shaped by its earlier history as an underground limestone cave, while simultaneously becoming part of a tropical environment. The steep walls created during collapse now descended into seawater rather than open air. Sunlight reflected across the surface above, while darkness remained deeper below inside the submerged structure. The formation itself records a sequence of events stretching across multiple climate periods. First, there was dry limestone terrain exposed during lower sea levels. Then, underground caves formed through rainwater erosion. Later, the cave roof collapsed into a sinkhole. Finally, rising seas flooded the structure and transformed it into the marine feature visible today. Water depth now influenced light levels. Marine organisms slowly began colonizing surrounding reef areas. Ocean conditions started shaping the submerged walls. Yet despite becoming part of the sea, the blue hole never lost the geological signature of its earlier dry period. The underwater sinkhole visible today still carries the hidden framework of the ancient cave system that existed long before Caribbean waters filled the region. As sea levels continued rising across the Earth after the Great Ice Age periods began fading, the ancient sinkhole beneath the Caribbean landscape became fully submerged beneath ocean water. What had once existed as a dry limestone depression, exposed beneath open skies, slowly disappeared below the advancing sea. The transformation unfolded gradually across long spans of time, as melting glaciers returned enormous amounts of water back into the oceans. Coastlines shifted inland, exposed reef platforms vanished beneath shallow tropical seas, and the collapsed cave system that would become the blue hole entered a completely new phase of existence. Once the sinkhole became permanently submerged, the surrounding environment began changing in important ways. Ocean water filled the deep limestone chamber, while marine conditions slowly shaped the structure from above. Sunlight now reflected across the surface where dry air once existed. Fish and marine organisms moved through waters above the submerged walls. Coral reefs gradually expanded throughout the surrounding region as the tropical environment stabilized. The ancient cave system had become part of the Caribbean Sea itself. Even though the blue hole transformed into a marine feature, the structure still preserved the physical shape created during its earlier history as a cave and sinkhole. The steep walls descending downward into darkness remained as evidence of the collapse that occurred long before seawater entered the area. The circular outline visible from above still reflected the geometry of the ancient underground cave system. From above, the blue hole appears like a natural part of the sea, yet nearly every major feature within the structure originated before the ocean flooded the area. The walls formed through cave collapse. The limestone developed through ancient marine sediments compressed over time. The underground chambers expanded through rainwater erosion, while the region remained dry land. Geological formations often act almost like archives, preserving evidence of older environments long after conditions change. Desert rocks may preserve fossils from ancient oceans. Mountain layers can reveal evidence of vanished rivers or volcanic eruptions. In the same way, the blue hole preserves clues from a time when the Caribbean coastline looked entirely different from today. The submerged sinkhole records the history of falling sea levels, exposed limestone terrain, underground cave formation, structural collapse, and rising seas, all within a single geological structure. The blue hole demonstrates how climate change, sea level shifts, erosion, and structural collapse can combine slowly to reshape entire regions. Water movement, chemical interactions, sediment accumulation, and marine life all became part of the evolving environment inside the structure. Conditions within the submerged sinkhole differed from the surrounding shallow reef because of the rapid change in depth. Sunlight reached only the upper portions effectively, while deeper areas remained increasingly dark. The structure had become both geological formation and environment at the same time. Ocean chemistry continues affecting the limestone walls below the surface. Sediments settle gradually into deeper sections of the hole. Water conditions shift with temperature, currents, and seasonal weather patterns. Even seemingly motionless landscapes remain part of an active Earth, where change continues constantly across long timescales. An island may seem fixed and unchanging across generations, yet geological history reveals that coastlines rise and fall, caves collapse, reefs grow, and oceans shift continually. The blue hole itself exists because the Earth never remains completely still. The submerged sinkhole also demonstrates how different Earth systems remain interconnected. Climate influenced sea levels. Sea levels controlled whether the limestone remained exposed or submerged. Rainwater shaped the underground caves. Structural collapse created the sinkhole. Marine ecosystems later developed around the flooded structure. Geology, climate, chemistry, water movement, and biology all became linked together within the history of a single location in the sea. Seen from above today, The blue hole almost appears isolated from the surrounding ocean because of its striking circular outline and darker color. Coral reefs surrounding the structure continue interacting with tropical ocean currents. Weather patterns influence water conditions above the reef. Marine organisms move through the region constantly. Human structures rarely survive more than a few centuries without maintenance, yet the geological framework of the blue hole records environmental processes stretching far beyond recorded history. Ancient caves formed underground, while glaciers covered large parts of the earth. Sea levels rose and flooded the landscape after climates warmed. Coral reefs later expanded around the submerged structure. The dark circular opening beneath the sea may appear calm and still from the surface, yet its existence depends entirely upon ancient movement and transformation. Rain dissolved limestone, underground chambers expanded, cave ceilings collapsed, oceans advanced across the land. Marine ecosystems developed around the flooded sinkhole. It serves as a connection between ancient dry landscapes and modern tropical seas. It preserves evidence of vanished Ice Age environments beneath modern ocean water. It reveals how slowly operating natural systems can create formations so large and dramatic that they remain visible even from space. Beneath the calm Caribbean surface, the blue hole preserves the history of an Earth that has never stopped changing. From high above the Caribbean Sea, the formation can appear surprisingly small because the surrounding ocean provides very few reference points for human eyes to judge distance accurately. Yet the blue hole stretches more than 300 meters across, making it one of the largest underwater sinkholes on Earth. A small boat floating near the edge often appears tiny against the enormous circular opening beneath the water. Standing near the rim can create a strange sense of scale because the darker center feels less like ordinary ocean and more like the entrance to an enormous submerged chamber hidden below the sea. In many tropical reef environments, the seafloor slopes downward gradually as shallow water slowly transitions into deeper ocean. Around the blue hole, however, the descent becomes sudden. Bright, shallow reef water gives way rapidly to much darker depths below. The contrast between the reef and the interior of the hole creates the impression that part of the ocean floor simply disappears downward into darkness. The walls inside the blue hole descend steeply into the water, forming vertical limestone surfaces that define the structure clearly. These walls remain one of the strongest visual clues, revealing the formation's earlier history as a collapsed cave system. Instead of sloping gently downward like a normal underwater valley, the edges drop sharply beneath the surface. Divers descending into the blue hole often describe the experience as swimming alongside a giant underwater cliff, where the reef suddenly falls away into deep blue darkness below. Steep vertical walls also influence how light behaves inside the structure. Near the upper edges, sunlight still reflects from the limestone and surrounding water, creating brighter conditions. As the descent continues deeper, however, less light reaches the interior. The walls begin fading into darker shades of blue and grey, while the bottom becomes increasingly difficult to see. Human eyes naturally rely on sunlight to judge space and depth, so the fading light inside the blue hole can create a strong feeling of descending into a separate, hidden environment beneath the sea. The nearly circular shape of the blue hole remains one of its most visually unusual features. Nature often produces irregular forms shaped by uneven erosion, shifting rock layers, and changing conditions. Rivers twist unpredictably across landscapes. Coastlines curve unevenly. Mountains rise in rough patterns rather than smooth geometry. The blue hole, however, appears remarkably circular from above. This symmetry reflects the shape of the ancient cave system that existed before collapse, and flooding transformed the area into a marine sinkhole. Circular formations naturally attract human attention because the brain recognizes them quickly against more irregular surroundings. The shape almost resembles a giant eye looking upward through the sea, or a perfectly cut opening placed into the reef itself. Combined with the dramatic color contrast between shallow turquoise water and the darker center, the geometry of the blue hole makes it instantly recognizable even in satellite images viewed from space. Few marine formations possess such a strong visual identity from above. Sunlight entering ocean water becomes absorbed gradually as depth increases. Bright colors disappear first, while deeper water absorbs more and more light. In shallow tropical reef environments, sunlight often reaches the seafloor clearly enough to illuminate coral structures and sandy bottoms below. Inside the blue hole, however, the rapid descent means sunlight cannot fully illuminate the deeper sections. The deeper water therefore appears darker and more shadowed from the surface. One container remains shallow, with bright light reflecting easily from the bottom. The other becomes extremely deep, so that the bottom disappears into shadow. Even if the water itself remains equally clear, depth alone changes how the human eye perceives color and brightness. The steep walls of the formation also create a sense of enclosure inside the structure. Divers descending along the limestone edges often remain close to the vertical rock, while the darker center stretches outward nearby. The walls serve almost like the sides of a giant underwater chamber, descending downward through increasingly dim light. Although the blue hole connects fully to the surrounding sea, the interior can feel visually separate because of the sudden depth and enclosing limestone walls. Geological structure strongly influences environments in ways humans may not immediately notice from the surface. The shape of the blue hole affects water movement, light penetration, oxygen distribution, and the types of organisms able to survive at different depths. The vertical walls create sharp environmental transitions rather than gradual ones. Conditions near the surface differ greatly from conditions deeper below. Even the sound environment changes with depth around steep underwater formations. Near the surface, waves, wind, and reef activity create gentle movement and noise throughout the water. Deeper below, those surface effects become more distant and muted. The descending walls of the blue hole guide divers downward into increasingly still conditions where darkness and depth begin dominating the environment. The circular form and steep limestone walls also preserve evidence of the sinkhole collapse that occurred during earlier geological periods. The ancient cave roof did not collapse into a scattered, irregular trench. Instead, the structure retained much of its original shape while sinking downward into the underground chamber below. Later flooding by rising seas preserved that collapsed framework beneath the Caribbean waters. The walls inside the blue hole descend steeply into the water, forming vertical limestone surfaces that define the structure clearly. These walls remain one of the strongest visual clues revealing the formation's earlier history as a collapsed cave system. Instead of sloping gently downward like a normal underwater valley, the edges drop sharply beneath the surface. Divers descending into the blue hole often describe the experience as swimming alongside a giant underwater cliff, where the reef suddenly falls away into deep blue darkness below. Steep vertical walls also influence how light behaves inside the structure. Near the upper edges, sunlight still reflects from the limestone and surrounding water, creating brighter conditions. As the descent continues deeper, however, less light reaches the interior. The walls begin fading into darker shades of blue and grey, while the bottom becomes increasingly difficult to see. Human eyes naturally rely on sunlight to judge space and depth, so the fading light inside the blue hole can create a strong feeling of descending into a separate hidden environment beneath the sea. The nearly circular shape of the blue hole remains one of its most visually unusual features. Nature often produces irregular forms shaped by uneven erosion, shifting rock layers, and changing conditions. Rivers twist unpredictably across landscapes, coastlines curve unevenly, mountains rise in rough patterns rather than smooth geometry. The blue hole, however, appears remarkably circular from above. This symmetry reflects the shape of the ancient cave system that existed before collapse, and flooding transformed the area into a marine sinkhole. Circular formations naturally attract human attention because the brain recognizes them quickly against more irregular surroundings. The shape almost resembles a giant eye looking upward through the sea, or a perfectly cut opening placed into the reef itself. Combined with the dramatic color contrast between shallow turquoise water and the darker center, the geometry of the blue hole makes it instantly recognizable even in satellite images viewed from space. Few marine formations possess such a strong visual identity from above. Sunlight entering ocean water becomes absorbed gradually as depth increases. Bright colors disappear first, while deeper water absorbs more and more light. In shallow tropical reef environments, sunlight often reaches the seafloor clearly enough to illuminate coral structures and sandy bottoms below. Inside the blue hole, however, the rapid descent means sunlight cannot fully illuminate the deeper sections. The deeper water therefore appears darker and more shadowed from the surface. One container remains shallow with bright light reflecting easily from the bottom. The other becomes extremely deep, so that the bottom disappears into shadow. Even if the water itself remains equally clear, depth alone changes how the human eye perceives color and brightness. The steep walls of the formation also create a sense of enclosure inside the structure. Divers descending along the limestone edges often remain close to the vertical rock, while the darker center stretches outward nearby. The walls serve almost like the sides of a giant underwater chamber, descending downward through increasingly dim light. Although the blue hole connects fully to the surrounding sea, the interior can feel visually separate because of the sudden depth and enclosing limestone walls. Geological structure strongly influences environments in ways humans may not immediately notice from the surface. The shape of the blue hole affects water movement, light penetration, oxygen distribution, and the types of organisms able to survive at different depths. The vertical walls create sharp environmental transitions rather than gradual ones. Conditions near the surface differ greatly from conditions deeper below. Even the sound environment changes with depth around steep underwater formations. Near the surface, waves, wind, and reef activity create gentle movement and noise throughout the water. Deeper below, those surface effects become more distant and muted. The descending walls of the blue hole guide divers downward into increasingly still conditions where darkness and depth begin dominating the environment. The circular form and steep limestone walls also preserve evidence of the sinkhole collapse that occurred during earlier geological periods. The ancient cave roof did not collapse into a scattered, irregular trench. Instead, the structure retained much of its original shape while sinking downward into the underground chamber below. Later flooding by rising seas preserved that collapsed framework beneath the Caribbean waters. Seen from above today, the blue hole appears calm and motionless within the reef system, yet its physical structure tells the story of dramatic geological transformation over time. The steep walls, sudden depth, enormous width, and circular shape all originated through natural processes acting slowly beneath the ancient limestone terrain long before the sea flooded the region. Every visual feature visible today connects to the formation's earlier history as an underground cave system shaped by water, erosion, gravity, and collapse. Rainwater slowly dissolved limestone underground. Structural collapse reshaped the landscape. Rising seas flooded the sinkhole and transformed it into an environment. The circular structure of the blue hole remains visible so clearly because depth changes the way light behaves beneath the ocean surface. From above, the reef reflects sunlight brightly through shallow tropical water, while the interior of the sinkhole absorbs much more light due to its sudden depth. The result is the famous contrast that makes the blue hole appear almost like a giant dark opening suspended within the sea. What seems at first like a simple difference in color is actually the visible effect of physics, depth, water clarity, and geological structure all working together at once. Sunlight entering ocean water does not travel downward forever. Water gradually absorbs light as depth increases, and different colors disappear at different rates. Red light fades first, followed by orange and yellow wavelengths. Blue light penetrates deeper than many other colors, which is one reason tropical oceans often appear blue to human eyes. In shallow water, enough sunlight still reaches the seafloor to reflect brightly back upward. In deeper water, however, much of that light becomes absorbed before it can return to the surface. The blue hole demonstrates this process very clearly because the depth increases so rapidly near the edge of the structure. Bright reef water surrounding the sinkhole may remain relatively shallow, allowing sunlight to illuminate coral, limestone, and sandy surfaces below. Just a short distance away, the interior drops downward steeply into much darker water, where sunlight becomes increasingly limited. The eye interprets this loss of reflected light as darkness, even though the water itself may remain extremely clear. In many shallow environments, sunlight scatters widely across the sea floor and surrounding water. Inside the blue hole, however, the sudden vertical drop creates a deep enclosed space where less light can penetrate effectively. The deeper portions remain shadowed beneath the reef structure, while the upper layers receive much stronger illumination from above. Near the surface, the water may appear bright and open with sunlight filtering downward in soft moving patterns. As depth increases, however, colors begin fading gradually. Bright reef tones become muted while the surrounding water shifts toward darker blue and gray shades. The limestone walls slowly disappear into shadow, while visibility ahead becomes more limited. This transition can feel similar to walking deeper into a massive stone building, where sunlight from outside grows weaker with every step inward. Near the entrance, everything appears bright and open. Farther inside, shadows begin dominating the environment, while details become softer and less distinct. The blue hole creates a comparable effect underwater because the structure controls how much light reaches different depths within the sinkhole. Bright, shallow water often feels welcoming because visibility creates a sense of safety and openness. Deeper, darker water tends to produce a different reaction because the limits of visibility become harder to judge. Human vision evolved primarily in environments filled with sunlight, so darkness naturally increases uncertainty. Inside the blue hole, the gradual fading of light creates a strong awareness of descending depth and hidden space below. Structure influences underwater conditions in many ways beyond appearance alone. Light availability affects temperature, visibility, oxygen movement, and the ability of organisms to survive at different depths. Near the surface around the blue hole, sunlight supports coral reef ecosystems and photosynthetic organisms that rely on light energy. Deeper inside the structure, lower light conditions create a different environment where fewer organisms can thrive easily. The physical shape of the sinkhole therefore helps determine the biological conditions developing within it. The walls of the blue hole also create zones where conditions shift rapidly over short vertical distances. In ordinary shallow reef environments, conditions may change gradually as water becomes deeper farther from shore. Inside the sinkhole, the descent occurs much more abruptly. Light levels decrease quickly, while temperature and water chemistry can begin changing as well. The steep vertical structure compresses these environmental transitions into a relatively concentrated area beneath the surface. Another reason the blue hole appears visually striking is because human eyes instinctively notice strong contrasts in brightness. A dark circular opening surrounded by glowing turquoise water creates an almost perfect visual separation between shallow and deep environments. The brain immediately recognizes that the darker area represents hidden depth beneath the surface, even without understanding the geological explanation behind it. This contrast explains why aerial photographs of the blue hole became so widely recognized long before most people learned how the formation actually developed. During calm weather conditions, sunlight moving across the surface can create shifting reflections over the upper layers of the sinkhole, while the deeper interior remains dark and stable below. Gentle waves distort the reflected light into moving patterns that drift across the surface above the vertical walls. The deeper sections remain visually still beneath the brighter upper water. In some ways, the blue hole almost resembles a giant lens where light, depth, and water combine to produce constantly changing visual effects. Even marine exploration equipment becomes affected by the changing light conditions inside the structure. Cameras, diving lights, and underwater mapping tools all respond differently as natural sunlight decreases with depth. Artificial lighting becomes increasingly important deeper inside the blue hole because sunlight alone cannot fully illuminate the lower sections. This fading light serves as a constant reminder that the environment within the sinkhole differs greatly from the brighter reef waters surrounding it. The circular sinkhole did not simply create an unusual visual landmark. Its steep walls and deep interior actively control the conditions existing within the water itself. Light decreases because of depth. Darkness increases because of structure. Environmental conditions shift because of geometry formed through ancient geological processes long before the sea flooded the region. The darker interior reflects the enormous depth of the submerged sinkhole and the limited ability of sunlight to penetrate far below the surface. The structure influences visibility, conditions, and biological activity throughout the formation. Every shadow visible within the blue hole connects to the ancient collapse of limestone caves and the flooded geological history preserved beneath the ocean today. Deep inside the blue hole, divers have discovered one of the clearest pieces of evidence proving that the structure once existed as a dry cave system above sea level. Hanging from portions of the underwater limestone walls are large stalactites formed long before the Caribbean Sea flooded the region. These mineral formations could only develop inside air-filled caves where water slowly dripped from ceilings over time. Their presence deep beneath the ocean's surface reveals a hidden chapter in the history of the blue hole that began during the ancient dry landscape of the Ice Age world. Stalactites form when mineral-rich water moves slowly through limestone rock and drips from cave ceilings into open air below. As the water reaches the ceiling of a cave chamber, tiny amounts of dissolved calcium carbonate begin separating from the droplets. Over long periods, these mineral deposits gradually accumulate into thin hanging formations extending downward from the ceiling. Each small mineral layer formed one drop at a time, while the cave remained dry above sea level. Water seeped through cracks in the limestone, carrying dissolved minerals collected from the surrounding rock. As droplets reached the cave ceiling and encountered open air, tiny mineral particles remained behind. Eventually, those particles built downward, layer by layer, into stone formations suspended inside the underground chambers. Some stalactites discovered inside the blue hole are remarkably large, showing that the cave system remained dry and stable for very long periods before flooding occurred. Large formations require enormous amounts of time to develop because mineral growth inside caves progresses so gradually. In many cave systems around the world, stalactites may grow only fractions of a centimeter over many years, depending on water flow and mineral concentration. The formations preserved within the blue hole therefore record long stretches of underground stability before rising seas submerge the region. The appearance of stalactites can vary greatly depending on water movement and mineral conditions within caves. Some develop as thin pointed structures resembling stone icicles hanging from ceilings. Others become thicker and more rounded as minerals continue accumulating over time. Inside the ancient cave system beneath the future blue hole, mineral-rich water slowly shaped these formations while darkness surrounded the underground chambers. Long before seawater entered the sinkhole, the caves already contained a hidden landscape of growing stone structures suspended beneath the limestone ceiling. The process responsible for forming stalactites depends upon a delicate balance between water, minerals, air, and time. If the caves had remained fully underwater during their formation, the stalactites could not have developed in the same way. Their existence proves that the cave chambers once contained air rather than seawater. Each droplet carried dissolved minerals collected while moving through cracks in the rock above. Tiny deposits remained behind with every drop. Over immense spans of time, those small deposits slowly accumulated into hanging stone formations extending downward through darkness. No sunlight reached these chambers. No ocean currents disturbed the still air inside. The caves existed as calm, isolated spaces hidden beneath the ancient Caribbean landscape. The stalactites also reveal how slowly geological processes can build enormous structures without sudden dramatic events. Humans often associate major landscape changes with earthquakes, volcanic eruptions, or violent storms, yet many of Earth's most remarkable formations emerge through tiny repeated actions working over time. The stalactites inside the blue hole formed through the simple repetition of water dripping from cave ceilings again and again across thousands of years. Patience alone transformed dissolved minerals into solid stone formations hanging beneath the earth. When divers first encountered these underwater stalactites inside the blue hole, the discovery provided strong confirmation of the sinkhole's ancient cave origin. The formations could not be explained by ordinary marine processes alone. Their shape and structure match stalactites found inside dry limestone caves across the world. Even though they now rest beneath ocean water, they preserve the memory of a period when the cave chambers remained exposed to air during lower sea levels. The underwater setting of the stalactites creates an especially unusual scene because two completely different environmental histories exist together within the same structure. The cave formations originated during a dry geological period shaped by rainwater and underground erosion. Later, rising seas submerged the chambers beneath tropical ocean water. Today, the stalactites remain suspended underwater inside a marine sinkhole, preserving evidence of conditions that vanished thousands of years ago. Mineral deposits inside caves often continue changing slowly, even after major environmental shifts occur. Water chemistry, temperature, and surrounding conditions can all influence how cave formations age over time. Inside the flooded blue hole, seawater now surrounds structures that originally formed in dry air-filled chambers. The environment preserves these formations while also placing them within an entirely different ecological setting from the one in which they first developed. The stalactites inside the blue hole can almost be compared to ancient architectural remains preserved beneath the sea. Just as submerged ruins may reveal evidence of earlier civilizations, these mineral formations reveal evidence of earlier landscapes and conditions. They show that the modern Caribbean Sea once stood far lower than today, and that dry limestone caves existed where deep ocean water now rests. The stone formations hanging beneath the surface therefore act like geological records preserved within the submerged sinkhole. Rainwater dissolved limestone and formed caves. Cave chambers expanded gradually underground. Mineral-rich water created hanging stone formations over time. Later, structural collapse reshaped the cave system into a sinkhole. Every phase unfolded through slow, continuous change rather than sudden creation. Even now, the underwater stalactites remain among the most fascinating features discovered inside the blue hole, because they connect the visible modern ocean to an ancient, vanished world. Deep beneath the calm Caribbean surface, these hanging stone formations preserve evidence of dry caves, underground darkness, dripping mineral water, and geological patience stretching far back into Earth history. The ocean eventually submerged the ancient cave system, yet the stalactites remain suspended within the flooded chambers, quietly preserving the memory of the world that existed before the sea arrived. The stalactites preserved deep inside the blue hole provide some of the strongest geological evidence explaining how the structure originally formed. These hanging stone formations confirm that the blue hole once existed as a dry cave system exposed above sea level long before the Caribbean waters flooded the region. Without these formations, scientists would still understand much about the sinkhole from its shape and limestone composition alone. Yet the stalactites offer direct physical proof of the ancient environment that existed before the ocean arrived. A desert may preserve traces of ancient rivers. Mountain layers may contain evidence of vanished oceans. In the same way, the cave formations inside the blue hole preserve evidence of a dry limestone world that no longer exists. Scientists studying formations like the blue hole rely heavily on physical evidence preserved within rock structures because geological history unfolds across timescales far longer than human memory. No person witnessed the caves forming beneath the ancient limestone terrain. No human observed the gradual collapse of the underground chambers or the slow flooding caused by rising seas after the ice ages ended. Instead, researchers reconstruct that history by examining clues left behind inside the formation itself. The stalactites act almost like signatures from an earlier environment. Their structure reveals that mineral-rich water once dripped through air-filled cave chambers. Their location deep beneath the modern sea proves that the caves existed before the region became submerged. Their size demonstrates that the cave system remained stable for very long periods during lower sea levels. Geological evidence inside the blue hole extends beyond stalactites alone. The steep limestone walls, the circular structure, and the underwater cave features all support the same conclusion about the sinkhole's origin. Yet the stalactites remain especially important because they are impossible to explain without a dry period above sea level. Ocean water alone cannot create hanging cave formations of that kind inside submerged chambers. Their existence confirms that the caves formed during an earlier stage when the region stood exposed beneath open air. The limestone itself records older marine conditions from long before the cave system existed. The underground erosion patterns reveal how rainwater dissolved the rock during lower sea levels. The collapsed sinkhole preserves evidence of structural failure underground. Finally, the flooded environment reflects the later return of rising seas after the Ice Age periods ended. Many landscapes lose evidence of earlier conditions after major environmental changes occur. Erosion, weathering, volcanic activity, and tectonic movement can destroy older geological records over time. Inside the blue hole, however, much of the ancient cave framework survived even after flooding transformed the environment completely. The preserved cave formations also remind humans how temporary modern coastlines truly are. Looking at the Caribbean Sea today, it can feel natural to assume the ocean has always covered the region exactly as it appears now. The stalactites deep inside the blue hole prove otherwise. They reveal that the sea once stood far lower than today, and that dry limestone caves occupied areas now submerged beneath deep tropical water. It reflects global climate cycles that change sea levels around the Earth. During colder Ice Age periods, water became trapped inside enormous glaciers, exposing large sections of continental shelf and limestone terrain. During warmer periods, melting ice returned water to the oceans and flooded those same landscapes beneath rising seas. The blue hole preserves evidence of both stages within a single geological structure beneath the surface. There is also something quietly fascinating about the idea that the deepest parts of the blue hole contain evidence from a vanished world hidden below modern ocean water. Divers descending into the sinkhole move through layers of environmental history without immediately realizing it. Near the surface, tropical marine conditions dominate the environment. Deeper below, the limestone walls and stalactites begin revealing clues from an ancient cave system that existed thousands of years before the present Caribbean coastline formed. Rainwater dissolved limestone gradually over time. Cave chambers expanded beneath the landscape, one small chemical reaction at a time. Mineral-rich water built stalactites through slow, repeated dripping. Cave ceilings eventually collapsed into a sinkhole. Rising seas flooded the structure after glaciers melted worldwide. Each stage depended upon time operating patiently across thousands of years. Tiny amounts of dissolved limestone carried by water eventually created underground chambers large enough to collapse. Slow climate warming eventually flooded entire landscapes beneath rising seas. The evidence preserved inside the sinkhole reflects the enormous power of gradual change. Its stalactites confirm the existence of ancient dry caves. Its structure reveals the collapse of underground chambers. Its flooded depths record the return of rising seas after the ice ages ended. The modern blue hole connects modern marine conditions to ancient geological environments that vanished long ago, yet remain preserved within the limestone beneath the sea. Even today, scientists study the geological evidence inside the blue hole because every preserved detail helps improve understanding of past climates, changing sea levels, and cave formation processes. The underwater sinkhole acts almost like a natural time capsule, where ancient conditions survived beneath the ocean long after the surrounding world transformed completely. Deep inside the darkness below the Caribbean surface, the blue hole preserves the memory of dry caves, ancient climates, and a changing Earth shaped continuously across geological time. The modern Great Blue Hole is not simply a deep hole filled with uniform seawater. Conditions inside the structure change gradually with depth, creating distinct underwater layers shaped by light, oxygen, temperature, and water movement. Near the surface, the water often appears bright and remarkably clear beneath the tropical Caribbean sun. Far deeper below, however, the environment becomes darker, quieter, and increasingly low in oxygen. The sinkhole acts almost like a vertical world where conditions shift steadily from one level to another as depth increases. At the upper surface of the blue hole, sunlight still penetrates strongly through the clear tropical water. Visibility in these upper layers can remain excellent during calm weather because the surrounding Caribbean Sea contains relatively low amounts of sediment compared with many coastal regions around the world. Sunlight reflects through the upper water in moving patterns, while the limestone walls near the surface remain visible beneath the bright blue sea. Fish and reef organisms often move through these shallower layers, where conditions remain more favorable for marine life. The surface water around the blue hole appears clearer, partly because sunlight continues interacting strongly with the upper ocean. Light energy warms the surface layers, while gentle wave motion and ocean circulation help keep oxygen mixed into the water. Wind moving across the sea also contributes to this mixing process. In many ocean environments, the upper layers remain relatively active because sunlight, weather, and surface movement constantly influence the water near the top. Sunlight becomes weaker with every descending meter beneath the surface. Colors gradually fade, while visibility decreases into darker shades of blue and gray. The deeper water begins feeling more enclosed because the steep limestone walls surround the interior of the sinkhole, while less light penetrates downward from above. The deeper water inside the blue hole also contains lower oxygen levels than the upper layers. Oxygen enters ocean water mainly through contact with the atmosphere and through photosynthetic activity near sunlit surface regions. In deeper isolated environments, where water circulation becomes more limited, oxygen levels can gradually decline over time. Inside the blue hole, the steep structure and depth help create conditions where the lower layers receive less oxygen replenishment from the surface above. This decrease in oxygen has important effects on the environment. Many marine organisms rely on oxygen-rich water to survive, so areas with lower oxygen levels tend to support fewer forms of life. Near the brighter upper layers around the rim of the blue hole, reef ecosystems remain active and biologically diverse. Deeper below, conditions become increasingly difficult for many organisms because darkness and reduced oxygen create a much harsher environment. Scientists sometimes describe these deeper low oxygen environments as oxygen poor zones, where biological activity becomes more limited. The deeper sections of the blue hole are not entirely lifeless, but they support far fewer organisms compared with the surrounding shallow reef system. The transition demonstrates how strongly conditions influence the distribution of life within ecosystems. Even within one relatively contained structure, conditions can vary dramatically from top to bottom. Near the base of a mountain, conditions may feel warm and humid. Higher elevations become cooler and less hospitable, while vegetation changes gradually with altitude. Inside the blue hole, depth replaces elevation as the controlling factor. Conditions near the surface remain bright and active, while deeper regions become darker, quieter, and more oxygen-limited. The steep limestone walls contribute heavily to these changing conditions because the structure restricts how water moves through the sinkhole. Open ocean environments often experience stronger mixing from currents, tides, and weather systems. Inside the blue hole, the enclosed vertical shape allows deeper water to remain more isolated from the surface layers above. This separation helps maintain the environmental differences between the upper and lower sections of the structure. Another important factor influencing deeper water conditions is the absence of strong sunlight far below the surface. In shallow reef areas, sunlight supports photosynthesis by algae and microscopic organisms that produce oxygen as part of their biological activity. Deeper inside the blue hole, very little light remains available for such processes. Without significant photosynthetic activity and with reduced water mixing, oxygen becomes less abundant in the lower layers. Near the surface, the water may feel open and brightly illuminated by sunlight. The deeper water can appear almost motionless compared with the brighter reef conditions near the upper rim. The descent feels less like moving horizontally through the ocean and more like entering a vertical sequence of changing environments. The darker appearance of the deeper water also reflects the combined effects of depth and reduced light penetration. Human vision depends heavily on reflected sunlight to interpret surroundings clearly. As light decreases, the environment begins losing color and detail. The lower sections of the blue hole therefore appear more mysterious, not because the water itself changes color dramatically, but because sunlight can no longer illuminate the deeper environment effectively. Water conditions inside the blue hole also continue responding slowly to weather, ocean circulation, and seasonal changes in the surrounding Caribbean Sea. Surface temperatures, storms, and shifting currents can all influence the upper layers of the structure. Yet the deeper sections often remain comparatively stable because the vertical sinkhole isolates them from rapid environmental mixing occurring near the surface. The structure creates a protected environment where different layers maintain distinct characteristics over time. The modern blue hole therefore contains not just geological history preserved within limestone walls, but also a complex vertical water system shaped continuously by depth, light, and oxygen availability. Bright, clear surface water transitions steadily into darker, low-oxygen layers far below. Marine life becomes less common with increasing depth, while conditions grow more isolated from the active tropical sea above. The structure formed long ago through cave collapse and rising seas now shapes the environment inside it every single day. The blue hole reminds scientists that physical structure and conditions remain deeply connected throughout nature. The steep walls, extreme depth, and circular shape created during ancient geological processes continue influencing how light, oxygen, and marine life behave inside the sinkhole today. What began long ago as a dry limestone cave system beneath an exposed landscape has become a layered underwater world where conditions shift gradually from bright tropical surface water into dark oxygen, poor depths hidden beneath the sea. Oxygen plays a critical role in ecosystems because most larger organisms require it to survive. Fish, crustaceans, and many other sea creatures rely on oxygen dissolved in seawater in much the same way humans rely on oxygen in the atmosphere. Near the surface of the ocean, waves, currents, and contact with air help replenish oxygen continuously. Deeper isolated water layers often receive far less oxygen exchange, especially inside structures where water circulation becomes limited by geography. Water layers inside the blue hole may also differ slightly in temperature and chemistry, depending on depth and circulation patterns. Surface water exposed to sunlight often becomes warmer, while deeper layers remain cooler and more stable. Ocean currents and storms influence the upper sections more strongly than the isolated lower depths. The vertical structure therefore creates a complex underwater system where different conditions remain separated across short vertical distances. Light availability remains one of the strongest dividing factors between these vertical layers. In the bright upper water, sunlight supports photosynthetic organisms that help form the foundation of reef ecosystems. Deeper below, reduced light limits how much biological productivity can occur. Without strong sunlight, fewer organisms can generate energy through photosynthesis, which affects the entire food system inside the deeper sections of the blue hole. Even though the deeper layers support less visible life, they remain important parts of the overall environmental system within the blue hole. Water chemistry, sediment movement, and microbial activity operate throughout the structure. The lower oxygen conditions help create a distinct environment, shaped by depth and isolation, rather than by active reef growth. Every layer inside the sinkhole contributes to the overall balance of conditions existing within the formation. While the deeper interior of the blue hole becomes darker and lower in oxygen, the reef system supports a more active environment filled with life. Around the outer rim of the sinkhole, sunlight still reaches the shallow reef clearly enough to support coral growth, algae, fish populations, and many smaller organisms that depend on tropical water. The contrast between the biologically active reef and the quieter interior depths is one of the most fascinating features of the blue hole, because two different environments exist side by side within the same region of the Caribbean Sea. The coral reefs surrounding the blue hole form part of a much larger tropical marine ecosystem extending across the waters near Belize. Coral reefs are often compared to underwater cities because they provide shelter, structure, food, and breeding areas for enormous numbers of marine organisms. Although coral may appear similar to rock from a distance, reefs are living biological systems built slowly by tiny coral polyps over time. Layer upon layer of calcium carbonate skeletons gradually accumulate until large reef structures emerge beneath the ocean surface. Near the outer rim of the blue hole, these reef environments create conditions capable of supporting remarkable biodiversity. Fish move through the shallower waters, searching for food and shelter among coral formations, while smaller organisms occupy cracks, ledges, and protected reef spaces. Sunlight powers photosynthesis in algae and microscopic marine life near the surface, forming the foundation for much of the surrounding food system. The warm, clear tropical water helps maintain stable conditions where reef ecosystems can continue developing slowly. The outer reef remains much more biologically active than the deep interior of the sinkhole because conditions there are more favorable for life. Sunlight remains strong enough to support photosynthetic organisms. Oxygen levels stay higher because the shallow water mixes more easily with the atmosphere and surrounding ocean currents. Water movement also helps transport nutrients through the reef system while maintaining healthier conditions for coral and fish populations. This difference between the reef and the deep interior can almost feel like comparing a busy coastal shoreline to a deep, isolated canyon beneath the sea. Near the reef, movement and biological activity remain relatively constant. Fish travel through the shallows, while reef organisms compete for space and resources. Deeper inside the blue hole, however, darkness and low oxygen create a far quieter environment where far fewer visible organisms can thrive easily. Many fish species spend time near the outer edges of the blue hole because the reef offers both food and protection. Coral structures create countless small hiding places that help smaller organisms avoid predators while also providing surfaces where algae and microscopic life can grow. Larger fish often move through these reef systems, searching for feeding opportunities along the edge of the deeper water. The steep drop into the blue hole creates an abrupt transition between reef habitat and open depth beneath the surface. The reef itself also acts as a physical boundary, separating the shallower marine ecosystem from the darker interior below. Sunlight reflects brightly across the upper reef, while the deep center of the blue hole absorbs much more light because of its depth. From above, this contrast between bright reef water and dark interior water reveals not only differences in depth, but also differences in biological activity and conditions. Coral reef ecosystems depend heavily on stability and balance. Water temperature, sunlight, oxygen levels, and water chemistry all influence reef health. In tropical environments like the waters surrounding the blue hole, clear, shallow seas allow coral organisms to receive enough sunlight for the microscopic algae living within them. These algae provide energy through photosynthesis, while the coral structures offer protection and habitat in return. The relationship forms one of the most important biological partnerships within tropical ecosystems. The reef surrounding the blue hole therefore supports much more than coral alone. Small fish, crustaceans, mollusks, sea fans, algae, and countless microscopic organisms all contribute to the overall ecosystem. Even organisms too small to notice play important roles within the reef food system. Tiny plankton drifting through the water become food for larger organisms, while algae growing across reef surfaces support grazing species moving through the shallows. Compared with the darker, lower depths of the blue hole, the outer reef environment often feels full of movement and color. Sunlight reflects from scales, coral surfaces, and drifting particles within the water. Reef fish may travel in groups through the upper layers, while ocean currents move gently across the coral structures. The deeper sinkhole nearby remains comparatively dark and quiet beneath the same tropical sea. The shape of the blue hole also influences how marine life distributes itself around the region. Many organisms remain concentrated near the rim and surrounding reef because those areas provide better access to light, oxygen, and food resources. Life therefore clusters more strongly around the outer structure rather than throughout the deepest sections below. Reef systems provide structure in environments that might otherwise remain open and featureless beneath the sea. The reef around the blue hole creates habitat complexity where different organisms can occupy different spaces, feeding areas, and protective zones throughout the shallow environment. The surrounding reef also protects portions of the blue hole from stronger ocean forces by helping reduce wave energy across the area. Coral reefs often function as natural barriers that shape water movement and create calmer conditions behind portions of the reef structure. This protective effect influences sediment movement, water clarity, and overall environmental stability throughout the region surrounding the sinkhole. The contrast between the active outer reef and the deeper interior of the blue hole demonstrates how strongly conditions shape ecosystems beneath the ocean surface. Bright, shallow reef water supports diverse marine life because sunlight, oxygen, and water circulation remain favorable. Deeper below, darkness and low oxygen limit biological activity inside the sinkhole. The geological structure created long ago through cave collapse and rising seas now determines how marine life distributes itself throughout the modern environment. It exists within a living tropical reef system where conditions vary dramatically across short distances. Around the rim, sunlight and coral support active ecosystems filled with movement and biodiversity. Farther below, the darker interior preserves quieter oxygen, poor conditions shaped by depth and isolation. Together, these contrasting environments create one of the most unusual underwater landscapes in the sea. Near the upper surface of the blue hole, sunlight continues supporting the biological systems that allow tropical ecosystems to thrive. Bright Caribbean light penetrates through the shallow reef water surrounding the sinkhole, reaching coral formations, algae, and countless microscopic organisms living near the surface. These upper layers remain biologically active because sunlight provides energy for photosynthesis, the process through which certain organisms convert light into usable energy. Without this steady supply of sunlight, the reef ecosystem could not maintain the rich biodiversity visible around the outer edges of the blue hole. Photosynthesis forms one of the most important foundations of life in shallow environments. Tiny algae living within coral tissues use sunlight to produce energy, helping coral reefs grow slowly over time. Microscopic plankton drifting near the surface also rely on sunlight for energy production. These small organisms may appear insignificant individually, yet together they support entire food systems extending upward to larger fish and marine predators throughout the reef environment. The warm, clear water surrounding the blue hole creates especially favorable conditions for sunlight penetration near the surface. In tropical seas, with relatively low sediment levels, sunlight can travel deeply enough to illuminate reef systems below. This allows coral reefs around the blue hole to remain productive and biologically active within the shallower upper layers of the Caribbean Sea. Fish move through these illuminated waters, while algae and microscopic organisms continue generating energy beneath the sunlight above. Far deeper inside the blue hole, however, the environment changes dramatically as sunlight fades with depth. The steep vertical walls and sudden drop into the sinkhole create conditions where light decreases rapidly below the surface. Without sufficient sunlight, photosynthesis becomes increasingly limited. Fewer organisms can produce energy from light, which reduces the amount of biological activity possible in the deeper layers of the structure. This gradual loss of sunlight helps explain why fewer species survive deep inside the blue hole compared with the reef. Near the upper rim, organisms benefit from oxygen-rich water, available light, and active reef ecosystems. Deeper below, darkness and lower oxygen create a much harsher environment. Many species adapted to bright, shallow reef conditions cannot survive easily in the deeper interior because the conditions change too dramatically with depth. Marine organisms living around the blue hole therefore adapt themselves to the conditions available within different layers of the environment. Reef fish remain concentrated near the upper regions, where food and oxygen remain more abundant. Coral organisms stay within shallow illuminated zones, where sunlight can still reach them effectively. Organisms capable of surviving deeper below must tolerate darker water, lower oxygen levels, and reduced food availability compared with the active reef above. Forest plants growing beneath dense tree canopies adapt to lower light compared with plants living in open fields. Animals surviving in deserts develop ways to conserve water, while organisms in cold climates adapt to lower temperatures. Around the blue hole, marine life adapts according to depth, light, oxygen, and water movement within the structure. The vertical nature of the blue hole makes these environmental changes especially noticeable because conditions shift so quickly across short distances. In some ocean regions, environmental transitions unfold gradually across wide stretches of seafloor. Inside the sinkhole, however, the steep walls compress these changes into a narrow vertical space. A short descent can carry divers from bright reef conditions into dark, low oxygen water where far fewer visible organisms remain. Sunlight powers photosynthesis near the surface, supporting algae, coral systems, and food webs throughout the reef. Deeper below, reduced sunlight limits energy production and biological productivity. Coral organisms rely on microscopic algae living within their tissues to help generate energy through photosynthesis. Without enough light, this partnership becomes difficult to maintain. Around the blue hole, coral growth therefore remains strongest near the shallow outer reef rather than deep inside the sinkhole where sunlight becomes too limited. Near the upper layers, movement, color, and biological activity remain visible throughout the reef environment. Farther below, darkness and isolation dominate the interior space. The sharp environmental contrast exists not because of geographic distance, but because depth changes conditions so dramatically within the structure. Even fish behavior often reflects these environmental boundaries. Many species remain close to reef structures where food, shelter, and oxygen remain more available. Open deep water inside the sinkhole offers fewer resources for reef organisms adapted to shallow illuminated environments. The environment surrounding the sinkhole also changes slowly over time through natural seasonal variation, ocean currents, and weather conditions. Storms may temporarily influence water clarity or movement near the surface, while deeper layers remain comparatively stable and isolated below. Yet despite these shorter-term fluctuations, the overall environmental pattern remains consistent. Bright upper layers support more active ecosystems, while deeper, darker conditions limit the amount of life capable of thriving there. The reef around the blue hole demonstrates this clearly. Sunlight supports photosynthesis. Photosynthesis supports reef growth and food systems. Reef structure provides shelter for organisms. Water movement supplies oxygen and nutrients. Deeper below, where many of these supporting conditions become weaker, biological diversity declines accordingly. The upper layers remain bright and biologically productive because sunlight continues supporting reef life and photosynthesis. Deeper inside the sinkhole, conditions become darker, lower in oxygen, and more isolated from the active tropical ecosystem above. Different depths create different opportunities for life, shaping the distribution of organisms throughout the structure. The surrounding reef thrives in warm illuminated water, while the deeper interior preserves darker, quieter conditions shaped by depth and isolation. Every organism living around the blue hole responds in some way to the conditions available within its part of the environment. Light, oxygen, water movement, and structure together determine where life can flourish within the remarkable underwater world surrounding the blue hole. The blue hole does not exist alone within the sea. It forms part of a much larger reef system stretching through the tropical waters near Belize, where coral structures have been growing slowly across immense periods of time. From above, the blue hole may appear like the main feature dominating the surrounding ocean, yet the coral reefs around it are equally important in shaping the environment of the region. These reefs create the bright, shallow waters surrounding the sinkhole, while also supporting the rich ecosystems living throughout the area. Coral reefs grow through the gradual accumulation of calcium carbonate skeletons produced by tiny coral polyps. Each individual coral organism is small and delicate, yet together they create structures large enough to become visible from aircraft and satellites high above the Earth. Layer upon layer of coral growth slowly builds upward and outward across the seafloor over thousands of years. What may appear from above as solid underwater rock is actually the combined result of countless living organisms working continuously across generations. The reefs surrounding the blue hole formed through this same slow biological construction process. Tiny coral polyps settled onto stable surfaces within the warm, shallow Caribbean water and gradually began building protective skeletons around themselves. As older generations died, new coral organisms continued growing upon the remaining structures below. Over immense spans of time, these repeated cycles created broad reef systems surrounding the submerged sinkhole and extending outward across the tropical sea. Warm temperatures, clear shallow water, and consistent sunlight all help support reef growth. The microscopic algae living within coral tissues require sunlight for photosynthesis, which provides much of the energy supporting the coral ecosystem. Without sufficient light or stable temperatures, coral growth becomes increasingly difficult to maintain. The shallow reef surrounding the blue hole therefore represents a carefully balanced environment, shaped by sunlight, water clarity, temperature, and ocean chemistry. Sunlight penetrates through the upper layers of the tropical water, while warm, stable conditions allow coral organisms to survive and reproduce. Ocean currents deliver nutrients and oxygen, while the reef itself provides shelter for many species moving throughout the ecosystem. Coral reefs often appear calm and motionless from above, yet they are actually highly active biological environments filled with constant growth, feeding, reproduction, and competition for space. Tiny reef organisms continue building skeletal structures slowly beneath the surface, while fish move through the coral formations, searching for food and protection. Microscopic life drifts through the water, while algae grow across exposed reef surfaces under the Caribbean sunlight. Every part of the reef contributes to the larger environmental system surrounding the blue hole. Tiny coral organisms working generation after generation slowly create underwater structures large enough to influence coastlines, water movement, and ecosystems across entire regions. Around the blue hole, the reef acts not only as habitat for marine life, but also as part of the larger geological and environmental framework shaping the area. The reef system surrounding the blue hole also demonstrates how biological and geological processes often become deeply connected in nature. The sinkhole itself, formed through ancient cave collapse and rising sea levels, long before coral reefs expanded around it. Later, ecosystems gradually developed throughout the flooded region, while coral growth reshaped the shallow surrounding environment. Geological history created the foundation, while biological systems slowly transformed the upper marine landscape over time. Coral reefs are also extremely sensitive to environmental change because the organisms living within them depend on stable conditions to survive. Even relatively small shifts in water temperature, chemistry, or clarity can place stress on reef ecosystems. Excessive heat, pollution, or changing ocean conditions may disrupt the relationship between coral organisms and the microscopic algae living within their tissues. When that relationship weakens, coral health can decline significantly. This sensitivity makes reef systems valuable indicators of conditions within tropical oceans. Healthy reefs often suggest stable water quality, suitable temperatures, and sufficient sunlight penetration. Declining reef systems may signal changes occurring within the surrounding environment. Around the blue hole, the condition of the reef reflects the broader health of the tropical Caribbean ecosystem connected to the formation. The reefs also influence the appearance of the blue hole itself by creating the bright, shallow water surrounding the darker center of the sinkhole. Sunlight reflecting from coral and limestone beneath the clear upper water produces the glowing turquoise colors visible from above. Without the reef system, the visual contrast defining the blue hole would appear different. The reef therefore contributes both biologically and visually to the identity of the formation. Coral reefs around the world are often compared to rainforests because both environments support extraordinary biodiversity within relatively concentrated areas. Countless species depend upon reef ecosystems for shelter, feeding grounds, breeding areas, and protection from predators. Around the blue hole, reef organisms occupy countless small spaces within the coral structures themselves. Every ledge, crack, and surface may support different forms of marine life interacting continuously beneath the tropical sea. The reef surrounding the blue hole also helps shape water movement and environmental stability throughout the region. Coral structures absorb portions of wave energy before it moves farther inward across the shallow environment. This protective effect influences water clarity, sediment movement, and conditions throughout the surrounding ecosystem. The reef acts not simply as passive scenery beneath the water, but as an active environmental structure, helping maintain the conditions supporting marine life nearby. Even though the blue hole often receives the most attention because of its dramatic appearance and geological history, the reef system remains equally essential to understanding the full environment of the region. The sinkhole and reef exist together as connected parts of a larger natural system shaped by both ancient geological change and ongoing biological growth. Coral reefs continue expanding slowly, while the blue hole preserves evidence of much older cave systems hidden beneath the sea. Coral depends on sunlight. Sunlight depends on clear water conditions. Reef organisms depend on coral structure for habitat and protection. Ocean currents influence nutrient movement and oxygen levels. Long ago, rainwater dissolved limestone beneath an exposed landscape and created underground caves that later collapsed into a sinkhole. Rising seas flooded the structure after the ice ages ended. Over time, coral reefs expanded throughout the surrounding tropical water and transformed the region into the vibrant environment visible today. Around the dark circular opening of the blue hole, the reef continues growing slowly beneath the Caribbean sunlight, one generation of coral at a time. The coral reefs surrounding the blue hole depend heavily on stable water conditions to survive and continue growing beneath the sea. The tropical reef environment around the blue hole functions through balance. When conditions remain stable, coral systems can continue supporting much marine life. When conditions shift too far outside those limits, the reef ecosystem may begin experiencing stress. Water clarity remains especially important for coral growth because sunlight must penetrate through the upper ocean layers to reach the microscopic algae living within coral tissues. These algae produce energy through photosynthesis and help sustain the coral organisms themselves. If water becomes too cloudy from excess sediment or pollution, sunlight penetration decreases and coral systems may struggle to maintain healthy growth. Around the blue hole, the relatively clear Caribbean water allows sunlight to reach the shallow reef effectively, helping sustain the surrounding ecosystem. Temperature also plays a major role in reef stability. Tropical coral systems generally thrive within a fairly narrow range of warm ocean temperatures. Water that becomes too cold or too warm for extended periods can place stress on coral organisms and disrupt the biological relationships supporting reef growth. The reef surrounding the blue hole developed gradually within stable tropical conditions where sunlight and temperature remained favorable for long periods. Ocean chemistry influences reef systems as well, because coral organisms rely on dissolved minerals within seawater to build their calcium carbonate skeletons. Tiny changes in water chemistry can affect how efficiently coral structures form and grow. Reef ecosystems therefore depend not only on sunlight and temperature, but also on the chemical balance of the surrounding sea. The Caribbean waters around the blue hole create conditions that have historically supported slow, steady coral growth across the reef system. What makes ecosystems especially fascinating is how interconnected everything becomes beneath the ocean surface. No part of the reef exists entirely alone. Coral structures provide habitat for fish and smaller organisms. Fish help move nutrients throughout the ecosystem. Algae and microscopic organisms support food systems near the surface. Ocean currents transport oxygen and nutrients through the region. The blue hole itself forms part of this larger interconnected system, even though its deeper interior differs greatly from the reef. The sinkhole influences water movement, conditions, and habitat distribution throughout the area. Fish move near the outer rim, while coral reefs expand through the surrounding shallow water. The geological structure, created long ago through cave collapse, now interacts constantly with the biological systems living around it today. Coral reefs are among the most biodiverse environments on Earth because they create complex underwater structures where countless species can survive together within relatively concentrated spaces. Tiny cracks, ledges, overhangs, and coral branches all provide habitat opportunities for different organisms. Around the blue hole, reef systems support fish populations, crustaceans, algae, mollusks, microscopic life, and many other marine organisms interacting continuously throughout the tropical environment. This biodiversity exists partly because reef systems create so many environmental niches within the same area. Some organisms remain hidden deep inside coral structures for protection, while others move freely through the upper water, searching for food. Certain species feed near the reef surface, while others stay closer to the seafloor. Different forms of life occupy different parts of the ecosystem according to their environmental needs and survival strategies. The structure surrounding the blue hole also helps support these ecosystems by shaping water movement and environmental stability across the reef. Coral formations influence currents and wave energy, while the shallow reef platform creates conditions favorable for marine life near the surface. Even the dramatic depth change around the sinkhole affects how organisms distribute themselves throughout the area. Life responds constantly to the physical structure of the environment beneath the sea. Forests provide shelter, food, protection, and breeding areas for countless species, while also shaping local climate and conditions. Coral reefs perform similar roles beneath the ocean surface. Without the reef structures surrounding the blue hole, much of the biodiversity currently living throughout the area would struggle to survive in the same way. Environmental balance remains essential throughout these interconnected marine systems, because changes in one area often affect many others. If coral growth weakens, habitat availability for reef organisms may decline. Changes in water quality can influence sunlight penetration and photosynthesis. Shifts in temperature may alter biological activity across the ecosystem. Marine environments function through relationships and interactions rather than isolated individual parts. The blue hole demonstrates this interconnectedness, especially clearly because the structure contains both biologically active shallow reef conditions and deeper oxygen-poor environments within the same formation. Near the upper rim, sunlight and oxygen support coral growth and marine biodiversity. Deeper below, darker low oxygen conditions limit the amount of life able to survive easily. Different parts of the structure therefore support different ecological conditions depending on depth and environmental stability. Life throughout the region depends heavily on the surrounding environment remaining within suitable ranges for survival. Coral requires sunlight and stable temperatures. Fish populations rely on reef structures for food and protection. Microscopic organisms depend on nutrient movement and water chemistry. Scientists often study reef systems because they reveal how sensitive ecosystems can become when conditions shift. Coral reefs respond closely to changes in temperature, chemistry, oxygen levels, and sunlight availability. Since reef organisms build their structures slowly across long periods, stable conditions remain especially important for maintaining healthy ecosystems over time. Around the blue hole, the reef system reflects both the beauty and fragility of tropical environments. The interconnected nature of the reef surrounding the blue hole also highlights how geological and biological history remain linked together beneath the sea. Ancient limestone caves formed below an exposed landscape long before coral systems expanded through the flooded region. Rising seas transformed the environment and created conditions where reefs could gradually develop around the submerged sinkhole. Coral reefs continue growing slowly beneath the Caribbean sunlight, while marine organisms move through the surrounding waters according to their environmental needs. The structure created through ancient geological processes now supports ecosystems that depend entirely on the balance of light, oxygen, temperature, and water conditions throughout the sea. For many years, much of the blue hole remained mysterious because the deeper interior was difficult for humans to explore. From the surface, the formation revealed only its dark circular outline surrounded by bright reef water. The steep walls and fade-in light below concealed much of the underwater structure from ordinary observation. Only through exploration by divers, scientists, and mapping technology did people gradually begin understanding what existed beneath the surface inside the sinkhole itself. Early exploration of the blue hole depended heavily on human divers descending carefully into the underwater structure to study its walls, depth, and cave formations. Diving inside the blue hole differs greatly from swimming in shallow tropical reef environments because the conditions change rapidly with depth. Sunlight fades steadily, while the surrounding limestone walls descend into darker water below. Oxygen levels decrease in deeper sections, while the environment becomes increasingly isolated from the active reef system near the surface. Divers exploring the blue hole often move slowly downward along the steep limestone walls, using specialized equipment designed for deeper underwater conditions. The descent can feel almost like entering another world beneath the sea, because the bright tropical surface environment gradually disappears overhead. As the water darkens, visibility changes and the surrounding structure becomes more enclosed. Ancient cave formations, such as stalactites, begin appearing deep within the sinkhole, revealing evidence of the dry cave system that existed before the region flooded beneath rising seas. Exploration inside the blue hole requires careful preparation because deeper environments create challenges for the human body. Pressure increases steadily with depth, while available breathing time becomes more limited. Divers must monitor depth, oxygen supply, ascent timing, and underwater conditions carefully throughout exploration. Unlike shallow reef diving where sunlight and surface visibility remain close by, deeper sections of the blue hole create a more controlled and demanding environment. Divers studying the sinkhole discovered the underwater stalactites that confirmed the cave system once existed above sea level during lower ocean conditions. The steep limestone walls revealed evidence of collapse and underground erosion. Every descent deeper into the structure helped scientists reconstruct the long geological history connecting ancient dry landscapes to the environment visible today. Mapping technology also greatly improved understanding of the blue hole over time. Early explorers relied mostly on direct observation and basic measurements while studying the structure. Modern scientific equipment allows researchers to create much more detailed maps of environments using sonar systems, depth scanning technology, and digital imaging tools. These methods help scientists measure the shape, depth, and internal structure of the sinkhole more accurately than earlier generations could achieve. Underwater mapping works by sending sound waves through the water and measuring how those waves reflect from surfaces below. Since sound travels effectively underwater, sonar systems can help researchers visualize underwater landscapes, even in dark environments where ordinary light becomes limited. Around the blue hole, mapping technology revealed the steep walls, circular structure, and deeper geological features hidden beneath the surface. The ability to map underwater formations has transformed ocean science, because so much of the seafloor remains difficult for humans to observe. Even though the oceans cover most of the Earth's surface, large portions of the underwater world remain far less explored than many land environments. In some ways, underwater exploration of the blue hole resembles exploring caves or deep canyons on land, except the environment is filled entirely with water and shaped by pressure, darkness, and depth. Visibility depends on light penetration, while movement requires careful control of buoyancy and breathing equipment. The steep walls and enclosed structure create a strong sense of vertical descent into an isolated environment beneath the tropical reef above. Technology has also allowed scientists to study conditions within the blue hole more closely. Instruments lowered into the sinkhole can measure oxygen levels, temperature changes, water chemistry, and sediment layers throughout different depths. These measurements help researchers understand how the vertical structure influences conditions inside the formation. Data collected from the blue hole contributes to broader understanding of ecosystems, underwater geology, and changing ocean conditions. One fascinating aspect of ocean exploration is how much remains unknown despite centuries of scientific progress. Humans have mapped large portions of the Earth's land surface in remarkable detail, yet vast regions of the ocean floor remain only partially explored. Deep environments can be difficult and expensive to study, because pressure, darkness, and distance create major technical challenges for researchers. Even today, new underwater discoveries continue reshaping scientific understanding of ocean systems around the world. The blue hole reminds people that hidden environments still exist beneath the surface of the modern world. From above, the formation appears calm and visually simple, yet below the waterline lies a complex geological structure preserving evidence of ancient caves, environmental change, and layered underwater conditions. Exploration gradually revealed these hidden details, one descent and one measurement at a time. Divers studying the blue hole have also contributed to public fascination with the structure because underwater photographs and exploration footage allow people to glimpse environments that would otherwise remain invisible. Images of steep limestone walls descending into darkness, underwater stalactites suspended deep below the surface, and the dramatic transition between bright reef water and darker depths all help communicate the unusual nature of the formation to people around the world. Modern exploration technology continues improving the ability to study difficult environments safely and accurately. Advanced diving systems, underwater vehicles, sonar imaging, digital mapping, and environmental sensors all help researchers gather information about structures like the blue hole. Scientific understanding expands gradually as new equipment allows deeper and more detailed observation beneath the sea. At the same time, the blue hole also serves as a reminder that the ocean remains one of the least fully explored parts of Earth. Large sections of the deep sea are still poorly mapped compared with many land environments. Extreme depth, darkness, and pressure continue limiting direct exploration in many marine regions around the world. Even well-known formations like the blue hole still contain environmental details and geological information that scientists study today. Divers descending into the sinkhole help reveal how caves formed beneath limestone landscapes long before rising seas flooded the region. Mapping technology uncovers hidden structural details beneath the water. Environmental measurements reveal layered underwater conditions shaped by depth and isolation. Beneath the calm Caribbean surface, the blue hole continues offering new opportunities to study a world that remained hidden for thousands of years below the sea. Scientific study of the blue hole continues even today because the structure preserves valuable information about geology, climate history, environments, and underwater ecosystems beneath the sea. Although researchers now understand much more about the formation than they once did, scientific knowledge rarely arrives all at once. Understanding develops gradually through repeated exploration, careful observation, new technology, and the steady accumulation of evidence over time. Researchers study the blue hole because the structure acts almost like a natural archive recording ancient environmental change. The limestone walls preserve evidence of cave erosion during lower sea levels. The stalactites reveal periods when the cave remained dry and exposed above the ocean. Sediments inside the sinkhole may contain clues about changing climate conditions and ocean history over time. Scientists studying these materials can reconstruct parts of Earth's environmental past by examining the evidence preserved beneath the sea. Geologists study the limestone structure and evidence of cave collapse. Marine scientists examine the layered underwater conditions and reef ecosystems surrounding the sinkhole. Climate researchers investigate evidence connected to changing sea levels and past ice age conditions. Oceanographers study water chemistry, oxygen levels, and circulation patterns within the structure. Ongoing studies also help scientists understand how environments change over time. Water temperature, oxygen levels, reef health, and marine biodiversity can all shift gradually as conditions change within tropical oceans. Repeated scientific measurements collected over years allow researchers to monitor patterns that may not become obvious during shorter observations alone. Long-term study helps reveal how stable or variable the environment surrounding the blue hole remains through changing ocean conditions. Modern technology continues improving the ability to gather information from difficult environments. Advanced sonar systems create detailed maps of underwater structures, while remotely operated vehicles allow observation of areas difficult for human divers to reach safely. Environmental sensors measure oxygen, temperature, salinity, and water chemistry throughout different depths of the sinkhole. Digital imaging systems capture detailed visual records of cave formations and reef conditions beneath the surface. Different water layers behave differently with depth. Geological structures preserve evidence from ancient climate periods. Reef ecosystems interact with changing ocean conditions near the surface. Rainwater dissolved limestone over time. Underground caves expanded slowly beneath the ancient landscape. Sea levels rose gradually after the ice ages ended. Coral reefs developed over thousands of years around the submerged sinkhole. The blue hole also attracts scientific attention because it represents a relatively accessible example of processes that occur in many other underwater limestone environments around the world. Studying the sinkhole helps researchers better understand cave formation, sea level change, underwater geology, and marine ecosystem development in broader contexts beyond Belize alone. Lessons learned from one location may help improve understanding of similar systems elsewhere across the oceans. It continues functioning as an active site of exploration, measurement, and scientific learning. Each study adds detail to the story of how ancient caves formed beneath exposed limestone terrain before rising seas flooded the region. Every environmental measurement improves understanding of the layered underwater conditions within the sinkhole. Exploration continues supporting human understanding of a structure shaped through climate change, geological time, and marine processes operating across thousands of years. The blue hole tells a story far larger than a single underwater sinkhole beneath the sea. Its formation connects geology, climate, ocean systems, cave development, sea level change, and ecosystems into one long sequence of environmental transformation unfolding across immense spans of time. What appears today as a dark circular opening surrounded by tropical reef water began as dry limestone terrain shaped by rainfall and underground erosion during ancient Ice Age periods. Long before the Caribbean waters flooded the region, rainwater moved through exposed limestone terrain and slowly dissolved underground cave systems beneath the surface. These were entirely land-based geological processes shaped by weather, gravity, chemistry, and time. Water seeped downward through cracks, while mineral-rich droplets formed stalactites inside dry cave chambers hidden below the landscape. At that stage, the future blue hole existed not as part of the sea, but as part of an exposed limestone environment connected to ancient climate conditions during lower sea levels. Climate played a central role in controlling every stage of this transformation. During colder Ice Age periods, enormous glaciers spread across large portions of the Earth and locked away massive amounts of water as ice. Because so much water remained frozen on land, global sea levels dropped significantly. Coastlines extended farther outward, while shallow marine regions became exposed terrain. The limestone landscape surrounding the future blue hole existed above sea level because Earth's climate at the time kept enough water trapped inside glaciers worldwide. Later, as global temperatures gradually warmed, those glaciers began melting slowly across long periods. Meltwater returned to the oceans, and sea levels rose again around the world. The exposed limestone terrain surrounding the ancient cave system gradually disappeared beneath advancing seawater. What had once been dry land transformed steadily into environment. The underground caves flooded, while coral reefs slowly expanded throughout the shallow tropical waters above. The stalactites reveal the earlier dry cave environment. The limestone walls preserve evidence of collapse and underground erosion. The flooded sinkhole records the return of rising seas after the ice ages ended. The surrounding reef reflects the development of tropical ecosystems after the environment stabilized underwater. Changes in global temperature influence sea levels. Sea levels determined whether limestone remained exposed or submerged. Exposure allowed rainwater to dissolve caves underground. Flooding transformed the collapsed sinkhole into a marine feature. Coral reefs later developed around the submerged structure as tropical conditions stabilized. Its origins belong to dry land geology, shaped by rainfall and cave formation. Its modern environment belongs to the tropical Caribbean Sea, filled with coral reefs, marine life, and layered underwater conditions. Both histories exist together within the same structure beneath the ocean surface. The formation acts like a preserved boundary between ancient land environments and ecosystems. Coral reefs growing near the surface depend upon stable water conditions, sunlight, and marine chemistry. The limestone structure below influences water movement and environmental layering inside the sinkhole. Ocean currents affect oxygen levels and reef ecosystems, while sediment slowly settles into deeper sections of the structure. Geological and marine processes remain interconnected continuously, rather than operating separately from one another. Looking at the Caribbean Sea today, it may feel natural to imagine the coastline and reef system as permanent features of the world. Yet the blue hole preserves evidence that the same location once existed as dry limestone terrain beneath open skies. A coastline may appear stable across generations while remaining highly temporary on the scale of Earth history. Mountains erode gradually, rivers shift course, coral reefs grow slowly, sea levels rise and fall through climate cycles. The formation also demonstrates how natural systems can preserve records of earlier worlds long after those environments disappear. The dry cave system vanished beneath the sea thousands of years ago, yet stalactites still hang beneath the water inside the flooded sinkhole. Ancient limestone landscapes disappeared beneath tropical ocean conditions, yet the geological framework remains visible within the structure. The blue hole preserves environmental memory inside the Caribbean Sea. Even today, geological and environmental systems continue interacting around the blue hole. Coral reefs expand slowly through biological growth, while ocean conditions shape ecosystems near the surface. Water chemistry influences reef health, while sediments settle gradually into deeper layers below. The structure formed through ancient climate-driven change remains part of an active, evolving environment rather than a completely static feature frozen in time. Beneath the calm blue surface visible today lies the preserved history of a world transformed repeatedly through climate, water, geology, and time. The blue hole connects dry land and ocean, ancient caves and modern reefs, environmental change and geological memory into one remarkable structure beneath the sea. Its dark circular form reflects not a single event, but a long continuous chain of natural processes linking Earth's atmosphere, oceans, climate, and geology together across thousands of years. Every stage of its history depended upon natural systems interacting continuously over thousands of years. The modern blue hole preserves the evidence of those transformations beneath the ocean surface, where ancient caves and environments now exist together within the same remarkable structure. Long before coral reefs surrounded the region, and long before divers descended into the sinkhole beneath the sea, the future blue hole existed as part of a dry landscape exposed during ancient ice age periods. Sea levels remained far lower than today because enormous glaciers locked away much water across the Earth. Rainwater slowly moved through limestone rock beneath the exposed terrain, while underground cave chambers expanded gradually in darkness below the surface. Tiny chemical reactions repeated continuously across thousands of years until large hidden cave systems formed beneath the ancient Caribbean landscape. Inside those underground chambers, mineral-rich water dripping from cave ceilings slowly created stalactites hanging downward through the darkness. The caves remained dry because the ocean stood far away from the exposed limestone terrain during those colder climate periods. Every stalactite preserved within the blue hole still carries evidence of that vanished world beneath the sea. Long before seawater flooded the structure, underground geological processes were already shaping the framework of the future sinkhole deep beneath the surface. Over immense spans of time, the cave chambers widened, while the limestone ceiling above them became increasingly unstable. Eventually, portions of the cave roof collapsed downward into the underground spaces below, forming a massive sinkhole exposed beneath open skies. Yet the transformation was not finished. Climate conditions across the Earth continued changing as ice age periods gradually ended and global temperatures warmed once again. As glaciers melted slowly around the world, rising seas flooded coastlines and submerged exposed limestone regions beneath advancing ocean water. The ancient sinkhole eventually disappeared below the Caribbean Sea, where it became transformed into a submerged marine feature connected to the surrounding tropical environment. Coral reefs slowly expanded through the shallow water around the flooded structure, while ecosystems developed near the surface above the darker depths below. The steep limestone walls preserve evidence of cave collapse and underground erosion. The underwater stalactites confirm the existence of dry caves during lower sea levels. Beneath the calm Caribbean surface, the blue hole preserves the memory of ancient climates, changing coastlines, and rising seas stretching far back into Earth history. The structure also reveals how deeply connected Earth's natural systems truly are. Climate influenced sea levels. Sea levels determined whether limestone remained exposed or submerged. Rainwater shaped underground caves, while later marine conditions supported coral reef growth around the flooded sinkhole. Geological processes and biological systems became linked together continuously across thousands of years. The blue hole formed not through a single event, but through a long chain of environmental interactions unfolding slowly. Coral reefs grow layer by layer beneath the sunlight, while ocean currents shape water movement throughout the region. Sediments settle gradually into deeper sections of the sinkhole. Marine ecosystems respond to shifting conditions near the surface, while darker oxygen-poor layers remain isolated farther below. The Earth never fully stops changing, even when those changes unfold too slowly for humans to notice during ordinary life. The tropical Caribbean environment visible today may appear permanent, yet the submerged sinkhole proves that the same region once existed as dry limestone terrain beneath ancient skies. Coastlines moved, oceans rose, caves flooded, coral reefs expanded. Entire environmental systems transformed gradually through climate and geological change over time. Ancient cave formations remain suspended underwater inside an environment. The limestone walls shaped by underground erosion now descend into tropical ocean water filled with reef life near the surface. Geological history and living ecosystems exist together within the same structure beneath the Caribbean sunlight. The modern appearance of the blue hole therefore reflects more than simple depth alone. Its dark circular form records the combined influence of climate cycles, rainfall, underground erosion, cave collapse, sea level rise, and reef development working across Earth history. Every stage contributed to the submerged landscape visible today beneath the sea. Scientific exploration continues helping humans understand these connections more clearly. Divers descending into the sinkhole observe underwater cave formations that reveal the region's earlier dry history. Mapping technology uncovers details hidden beneath the dark water below. Environmental studies measure changing oxygen levels, reef conditions, and layered environments shaped by depth and structure. The blue hole remains both a preserved geological record and an active site of scientific discovery beneath the ocean surface. At the same time, the formation still preserves a sense of mystery because the ocean itself remains only partially explored. Large portions of the underwater world continue hiding beneath darkness, depth, and distance from ordinary human experience. The blue hole stands as one visible reminder that Earth still contains environment shaped through ancient natural processes operating far beyond the timescales of everyday life. Beneath the bright waters surrounding Belize rests the preserved history of a changing planet. Rain dissolved limestone underground, while glaciers lowered sea levels across the Earth. Cave chambers formed in darkness beneath exposed land before collapsing into a giant sinkhole open to the sky. Rising seas later flooded the structure, while coral reefs slowly expanded throughout the surrounding environment. What remains today is not simply a hole beneath the ocean, but the visible result of climate, geology, chemistry, water, and time working together across thousands of years. Ancient caves survive beneath modern ocean water. Reef ecosystems flourish around the rim, while darker depths preserve quieter conditions below. Every layer of the structure reflects a different chapter in the environmental history of the Earth itself. Long after the ancient dry landscape disappeared beneath rising seas, the blue hole continues preserving the evidence of those vanished worlds within the limestone beneath the water. Thank you for listening to the Sleepy Mind channel. I hope you enjoyed learning about the Great Blue Hole and the ancient geological history hidden beneath the sea.